Hello, and welcome to today's online panel discussion on unlocking new sensing capabilities with mid-infrared PICs. My name is Mark Elliott. I'm the COO of Europa Science, which is the publisher of Electro-Optics. We're going to spend the next hour or so discussing how mid-infrared photonic integrated circuits are reshaping sensing applications and what's really needed to scale them successfully across a range of industries. Mid-infrared photonic integrated circuits, or PICs as we all know them, already are offering transformative potential across industries by enabling highly sensitive, compact, and scalable optical sensing. These advanced devices are uniquely suited, of course, to detect a wide range of gas molecules, unlocking powerful applications in environmental monitoring, industrial safety, digital health, automotive systems, and so many more. So while there's a lot of potential out there, there are also a lot of challenges, and there are some obvious questions for us to answer. Critically, of course, how do we scale up these solutions from lab prototypes to robust market-ready products? And what hurdles do manufacturers, engineers, and application developers face along the way? This online panel discussion will delve into these challenges and look at how they're being encountered by manufacturers and those teams developing and deploying them. And we're looking at the key benefits that these mid-infrared PICs can bring to various use cases and notable innovations being utilized. If it sounds like an ambitious program, you are right there. But I'm very happy to say we've got four people to help me unpick this topic, and they really know what they're talking about. I'm going to start off by introducing Richard Pyramidovich. He is our first guest. He comes from Vigo Photonics, who it is also timely for me to say thank you. They're our partners on our online panel discussion today. Without them, this wouldn't be happening. So thanks again for their help with this. Richard is obviously the PIC program director at Vigo Photonics, and he's the leader of the HyperPIC project, which is driving the development of fully functional photonic integrated circuits operating in the mid-infrared range. Richard is an associate professor and the head of the optoelectronics division at Warsaw University of Technology, where he spent his career advancing optical spectroscopy, solid-state lasers, and fiber optic communications. He's also the co-founder and CEO of Lighthouse, which is Poland's first integrated photonics design house. So it's a true bridge there between academia and industry, with loads of scientific publications across more than 30 R&D projects. He's a real kind of heavyweight in this space, and his impact is being felt in Poland, but obviously far beyond that. So welcome, Richard, and thanks again to Vigo Photonics for helping us put this on. My next guest, or next panelist, I should say, is Abdul Rahim. He is the ecosystem manager at Photon Delta, where he's overseeing a network of more than 70 organizations working to build a thriving photonics industry. He's got a PhD in silicon photonics from TU Berlin and a degree in innovation management from HEC Paris, and obviously has a really sharp sense of how this works in terms of collaboration and growth strategies. Before joining Photon Delta, he transformed ePIC's Fab from the world's first MPW broker for silicon photonics into a global alliance. He also co-leads the Integrated Photonic Systems Roadmap International, which is guiding the industry's long-term vision. I should say both he and Richard are in the Photonics 100. Abdul joined us in 2024. Richard joined us just this year gone, so welcome to you both. And another introduction is to Ruud Oldenboving, who is a principal scientist at IMEC and another Photonics 100 honoree. He is certainly one of the leading minds in laser physics and photonic integration, and has worked for more than 17 years in integrated photonics and more than that in terms of laser research. He has been instrumental in advancing hybrid integration, combining INP and SIN to create ultra-narrow line width tunable lasers directly onto photonic chips. It's got a lot of scientific papers to his name. It's got 10 patents. And as I said, he has been in the Photonics 100 for a year or so. So thanks again to Ruud for joining us again on this. And last but certainly not least, we are joined by Dr. Emre Kaplan, who is the PDK manager at Cornerstone, based out of the University of Southampton, which is a leading platform for open access silicon photonics innovation. Emre holds holds an MSc in electronics engineering from the University of Bologna and a PhD in integrated photonics from the University of Ferrara. Over 5 years of experience designing PICs across multiple material platforms from silicon on insulator and silicon nitride to indium phosphide. And he's been working across a number of different organizations across Italy, Netherlands, and France. And he is currently at Cornerstone driving the process design kit, or the PDK development, which is helping researchers and companies bring new photonic technologies from concept to fabrication. Just a bit of housekeeping before we get on to the real issue of the day, which is these online panel discussions are designed to be useful and interactive. We would really welcome any questions from you too, so please submit them at the bottom of your screens, and I'll do our very best to get them tackled across what I hope will be a very full and lively discussion. Right, we are going to warm everybody up by kind of asking people to give us a bit of an introduction. I'm going to start with you, Richard, and I'm going to ask this question to everybody on the panel. But could you kind of share any projects in this sector which you are excited about? Anything recently that you think our audience should hear about? So over to you, Richard. Thank you.
Thank you, Mark. Thank you for that kind introduction and this very question specifically. Because, well, in an obvious way, I have to mention the HyperPIC project, which is managed by Vigo Photonics within the IPCEI, Important Projects of Common European Interest Mechanism, and it's about defining the whole value chain for the mid-IR photonic integrated circuits, and then finally, in a long perspective, developing also the first of its kind foundry here in Poland, but serving to all Europe. Apart from that, I have to mention also several local initiatives preceding HyperPIC, which was because we have started 4 years ago with first initiative, first technological project oriented toward investigating the problems and challenges with respect to that part of the spectrum. It was called MIRPIC, mid-infrared photonic integrated circuits, and also some products oriented locally funded project. But last but not least, I have to mention about PICs Europe, the biggest initiative in Europe related with photonic integrated circuits pilot manufacturing line. We are a part of that as a Poland, as a Warsaw University of Technology, and it is closely connected to what we are trying to do in Vigo Photonics within HyperPIC. Sorry for being too long a little bit.
Not at all. I mean, the problem with this topic, of course, is there's just so much to talk about, which is probably reflected in the number of people that have signed up to hear it. So thank you for that very kind of whistle-stop overview of a lot of activity. Emre, I'm going to come to you next, if I may.
Yeah, surely. Yes, please.
Yep, that's fine. Yeah, just talk. Yes, absolutely. So kind of any projects that you would like to share with the group?
Yeah. So there is a project called Mission. Professor Goran Mashanovic at the Optoelectronic Research Center at the University of Southampton, his team are working on photonic integrated circuits that at mid-IR range. They are trying to create some new applications in like CO2 detection in ocean. And also very recently, I got a catch-up meeting with them as well. So they are working on the lung cancer cells detection. So it is really crucial for early diagnosis. They work with the University Hospital. They use their facilities and database. So the mission project is using like some type of technology platforms. They operate mid-IR wavelengths for mid-IR sensing applications. So the project is still going with a collaboration, and it's a pure academic research program, but of course the outcomes will be useful for the future developments.
Yeah, and will as far as you're aware, will people be able to access that data and that kind of research work as it's going, or are they waiting to reveal the findings at the end?
As they progress, they actually share the outcomes already at conferences and on journal papers. But of course, when you develop a new system for sensing applications, you need to have some trials, more data to get accuracy. So this is still ongoing project, but people will be will have access what is generated and what know-how generated through this program.
Okay. And I should say just quickly that if anybody wants details of any of these projects, just drop us a note in the chat and we can contact you later on and share those details at the end. Okay, I'm going to come to you, Abdul. Anything you would like to highlight that you've read about or participated in?
Yeah, this is interesting for us as Photon Delta, which is my organization here. We are in a phase of now setting up the phase 2 of our program. And as you mentioned in my intro, that we have 70, 80 organizations in our ecosystem. And interestingly, we also have something more than 20 fabless chip companies in our ecosystem. And several of them are actually looking at mid-IR technologies for sensing, say healthcare or on environmental sensing. And while Photon Delta is a Dutch organization and it's a public-private partnership, and in the Netherlands there are certain topics related to environmental sensing, which are very relevant, for example, related to, and sometimes they are related to, in general, the atmospheric gases which are being sensed, CO2 or nitrogen, but also related to agri-food, for example, about soil conditions. This is more geared towards smart farming, for example. Right, so these are different applications which we as Photon Delta which we are supporting as Photon Delta, our organizations to mature, to take these technologies from early stage research and then commercialize it, which is more or less the objective of this growth fund as well. And in the past developments, actually, our partners have developed very nice building blocks, and now we are looking into that how could we bring all the pieces of the puzzle together into a working system. Of course, chips are very important. This is one fundamental part of the solution. You can call it the heart of the solution, but then there are a lot of bells and whistles which are also necessary to convert this chip into a system. So this is where most of our energies as Photon Delta and our partners and National Growth Fund are actually gravitating now.
Okay, yeah, absolutely. I mean, it's always the way, isn't it, when we're discussing issues around technology development in photonics? It's such an integrated kind of ecosystem of different kind of application opportunities, but also the technology structures that kind of go behind that are pretty complex and interconnected, as you say. Talking of the Netherlands, let's go to Ruud. Please share any kind of things you particularly wanted to highlight to the audience. Thank you.
Sure. So we have a few running projects, but mostly it's industrial interest that I see. So there's interest coming from big companies, mostly focusing on gas sensing, and then it's at this moment in time it's a big deal in at least the Netherlands, and I'm assuming in whole of Europe. That cattle is producing too much methane, too much CO2, too much nitrogen. But it's difficult to measure it, and it's especially difficult to measure it continuously. So that's turning out to be a very interesting market to continuously monitor what the outgassing of different things are in especially in barns. At the same time, what we see is there's an interest, and there has been an interest for a long time. So without naming and shaming, some companies have gone bankrupt over it, but there's still some glucose sensing interest for smartwatch applications. And that seems to be another high potential volume market that really needs the mid-IR spectrum.
Yeah, absolutely. That's a nice segue. Thank you again to that. So I wanted to talk about that kind of mid-infrared spectrum wavelength. And what do you think is the summary of why it's so conducive to sensing compared to other wavelengths, particularly such as visible and near infrared? What makes this the banker spectrum to kind of go with? Ruud, as I've got you on, do you want to try and answer that one for me? Why mid-infrared spectrum wavelengths are so good at sensing? What is it?
Well, physics.
Yep.
Right. It's or maybe chemistry even. So it's really the the absorption spectrum of the molecules that we're interested in, and certain very interesting molecules have a very distinct fingerprint in the mid IR, and that helps, for example, in parts per million measurements, but it also helps in detecting certain quality. When you look, for example, towards milk measurements, it really you need a very broad spectrum to measure, and very broad spectrum in the more visible range gets absorbed by the water in the milk. So you have to go towards the higher end of the spectrum in order to look at the interesting features of the milk, but not of the absorbing water or other materials.
Yeah. And then Richard, coming back to you on that kind of question. I mean, you've obviously, particularly in your kind of academic research, must see a range of scenarios where people are playing around on the edges of this. Where does that kind of experimentation go wrong, and why, therefore, is this mid-range so critical, do you think?
Starting from my background, I spent a number of years in doing some classical spectroscopy using very nice visible light mainly. So it was a pleasure in the lab because everything was seen. However, moving to mid-IR offered access to all those vibronic transitions mentioned by Ruth, which enable in a very precise and distinctive way to determine the presence of individual chemical substances. Optimally in gaseous media, however, also liquids are of concern quite easily. And as Ruth mentioned, the glucose monitoring in a smartwatch or very compact system is a kind of holy grail of that technology, and it is really blowing the mind. So that's the reason of moving to mid-IR, which defines a lot of challenges instead of a pleasure of being in the lab. So it's a painful experience to manage everything using totally invisible light and also so hard to detect, to be honest.
Yes. It's interesting, isn't it? I mean, it's a joy, I suppose, trying to push boundaries, but the pain of kind of hitting those kind of barriers and the the sort of challenge of things not working the way you want them to
is painful, and then my PhD students can easily confirm that. But it is also extremely attractive from the point of view of applications.
Yeah. And then Abdul, I mean, obviously you have a kind of visibility across a range of different organizations using this sort of technology. Do you think it's well understood its kind of core sort of, I suppose, strength or kind of purpose? I mean, are you seeing kind of organizations still pushing at those boundaries and trying to do things that, fundamentally perhaps are ill-judged?
I cannot say that if it is ill-judged or not, but what I mean, as compared to some of the other applications, I should not say many others, but some of the other applications, maybe mid-IR applications are still have not entirely commercialized. There is a big effort going on, and I think that my organizations and other organizations of my type should enable all the organizations which are trying to build solutions through on mid-IR platforms, and I think both Richard and Rod have mentioned several reasons that why mid-IR is interesting, and they have also mentioned some applications where mid-IR makes a lot of sense. And I think just to complement or add on to what they have already said, I think the whole purpose of integrated photonics is that, for me at least, I see it is the most viable route to commoditize photonics in the form of photonic chips, and this commoditization, then you have the scaling factor from the foundries, and you have the compactness factor. You can put it even in a smartwatch, and in a smartwatch or in a very compact manner. And what it all leads to is also that, as you know, that today the only biggest driver is datacom and telecom applications, transceivers. And I think the whole technology of integrated photonics should not hinge only on one key application, datacom and telecom. And other applications enabled by mid-IR actually de-risk the long-term sustainability and growth of this technology.
Okay.
So looking from the long-term, sustainability of our technology, integrated photonics for its growth, and when we say that, okay, we would like to have infrastructure on the foundry side, on the packaging side, testing, assembly, everywhere, somehow we have to keep them fully loaded. And probably transceivers are not the only application which can fully load this infrastructure. So it is very important to nurture these new applications on mid-IR platforms.
Yes.
Of course, then there are some specificities. It is not a direct one-to-one translation of what we do in near infrared on mid-IR. There are some very specific challenges, and I think these are in some cases being very well explored, and some are still outstanding. And in that sense, I think it is still a very exciting topic. If someone wants to commercialize some solution, it is exciting on that front also. And if someone wants to, solve some research curiosities, it also offers a lot of opportunities there. So I think it is really technology which is at the interface of, I would say, industry and research. So it all makes it very exciting in my view.
Okay, thank you. I've had a question come in already while we've been talking, and it's a perfect segue into. I think actually this person has actually been looking for the questions we've been working on for here. So it's about the scaling up of mid-IR PICs from lab to mass market products, and I'll go to you, Emre, because obviously Cornerstone is kind of part of this sort of project to kind of commercialize and scale, but what are the biggest challenges that manufacturers are facing when trying to develop these sensing solutions? And, is there a kind of an early sense of which application would be the first to really drive this transition? So it's a big question. I'll hand over to you, Emre. Thanks.
Yeah, surely. So if you look at the semiconductor foundries in general, as others emphasize, they are really designed to manufacture photonic chips for telecom and datacom applications. So we are stick at the fabrication processes which are already well established, let's say CMOS compatible with for the near infrared wavelengths. But there are some limitations, like we use always this claddings in manufacturing. When we do any waveguides in any platform, they are actually sandwiched by oxide layer. That actually prevents to reach up to longer wavelengths, because 4 micron and longer wavelengths will be quite absorptive in the oxide layer. So first of all, you just need to get rid of, if you are interested in silicon photonics doing telecom, but at the same time mid-IR applications, then you just need to adjust your fabrication process accordingly. Or choose another material platform, like germanium is a popular material for mid-IR applications, but it has some technical issues, like it has crystal mismatch with silicon. So if you deal with germanium wafers in the lab, so you need to actually double careful while handling, because the wafer can be cracked very easily. To scale it up, of course, you need whole ecosystem in general. So it is not about designing waveguides only, high quality devices, but also the packaging is quite important, because we are talking about sensors. They may be deployed in places with severe conditions. So your PICs should be working and adaptive to, let's say, environmental turbulences first. So in order to do that, you need to have multiple trials in fabrication. Of course, optimize your device first, and then having a proper packaging for your chip that needs to be in the market in the real world. So these are the main challenges for scaling up the mid-IR chips. One more thing actually is the laser sources as well. So you can use some external hybrid integration of laser sources on chip. These are mostly 3.5 or QCL, quantum cascade lasers. but we know that 3.5 and these cascade lasers, quantum cascade lasers, are not fully CMOS compatible. So there should be some work in the fabrication side if you really want CMOS compatible devices for scaling up. Of course, you need to find a foundry that provides, I don't know, like 8-inch or 10-inch wafer manufacturing.
Okay. Thank you. Yeah. Interestingly, I mean, you mentioned about laser sources here. I mean, I think this question is kind of aimed primarily at Ruud, but I'll go to you next if that's okay. But Ruud, I mean, there's a question that's come in about how far you think the industry is with integrated laser sources. I mean, how integrated is it, and particularly at your organization, what would your answer be to that?
Not very far.
Okay. And what
So the thing is, it takes a long time to fabricate a laser, especially on chip. And there's so many interesting things to look at. You cannot do everything at the same time. And typically, when you're looking at integrating a light source onto a photonic chip, you're bound by the bandwidth of your semiconductor. In the near to mid IR, typically you're then limited to about maybe 100 nanometer bandwidth, and beyond that you would need a second, third, fourth semiconductor device, and you need to route it cleverly on your chip. So it becomes way more difficult, and especially when you compare it to, let's call it the old-fashioned type of lasers, like optical parametric oscillators, OPOs. There you had a very, very broad range of wavelengths, but again, those are also really, really, really difficult to control. These were I remember working on those, when the world was still black and white, like over 20 years ago, and they were a pain. So in that sense, I do see a lot of interest going towards the semiconductor part, and then but yeah, how far are we? Generically, I would say it's just engineering, but it's not as easy as it sounds.
No. Okay. No, that's
Does that answer the question?
It does. It does. It's hopefully the person that asked that, who's watching will think. So if you've got a supplementary, please drop it into the chat box and we'll try and get to it. I want to kind of just jump around a little bit if I could. I wanted to ask about just general kind of scaling up, the challenges that manufacturers are facing. So just go back to that question about the mid-IR PICs. Richard, I mean, anything that you would highlight from all of your work around where you feel the sort of the biggest hurdle sits?
Honest, what I have learned after 4 years of attempts to developing the technology of mid-IR photonic integrated circuits is that mid-IR peaks are built on challenges only. So it's a number of challenges not only related with scaling up, but with managing the fundamental functionality. So connecting all those pieces together, light sources of extremely low efficiency, because quantum cascade lasers are not the lasers like typical semiconductor lasers of efficiency, of quantum efficiency exceeding 90%. Quantum cascade lasers limit of efficiency is about 20% or stuff like that. So this means that you have a number of heat to be dissipated from that CW operating laser. ICRs are much better. However, they are limited with respect to the spectral range because they can go up to 6 microns, and that's the upper limit at that moment. So also, if you are considering the sensing features, you have to totally change the paradigm of designing the wave guiding elements of photonic integrated circuits, because in classical PICs dedicated to datacom or telecom applications. You are designing the waveguides just to provide the functionality of properly guiding the light. In the case of sensing waveguides, you have to push out the guided mode to expose the mode to interaction with the environment. So the paradigm of designing the waveguides is totally different in that sense. Plus, you have to introduce some detectors able to detect the mid-infrared radiation. Typically, we are using in Vigo Photonics antimonide based detectors. However, there are also other options, obviously. However, putting all those components all together on a single chip is a first challenge. The second is provide proper technique of packaging, considering the mechanical packaging, electrical packaging, thermal packaging, and so on and so forth, and finally to provide the final device in a form acceptable by the client and attractive to the market. So it's a number of challenges, from the very fundamental issues of design to the issues of having all those components all together and ready to the market. So, and plus funding, which is the challenge which defines the biggest possible limiting factors.
Yeah. We have a phrase in English called "this isn't an area for the faint-hearted," so quite a challenging set of circumstances to overcome. Abdul, I'd wanted to come to you. I mean, obviously, we've heard a lot about the challenges. Would you kind of agree with Richard that is the basic default with this, or are there any particular kind of success stories or easier paths that you could bring to the table?
I don't know if there are any easier parts. I think for sure there are a lot of challenges, and I think we talked about scaling up. This is more on the supply side. I look more on the demand side. Things become more easy if there is a drive from the demand side, and then things go hand in hand. So I think solving all these challenges, which all the other colleagues mentioned here, like Emre and Ruud and Richard, I think these are all very important problems to be solved, and also then you need associated funding to solve these challenges. I think in parallel, it is important to have at least one anchoring killer app for mid-IR photonics, which can then it should not only be a technology push, but there has to be an associated market pull as well. So this is not entirely clear today. There are a lot of prospect applications, some low volume, some mid volume, and some really very high volume. And I think once one killer app appears, then I think this scaling from the supply side and then matching it with the demand side become more natural, I would say. We have seen it in the case of transceivers. Okay, the metric there is higher speed and higher speeds, and then energy became important, and then with AI latency became important. So there is one application which is driving the underlying supply chain. The underpinning supply chain is all reacting to the demands of that one app.
Yeah.
Right. So somehow I think for mid-IR, I think it will happen. It's just a matter of time that there will be at least a few killer apps which will drive this all up. In many cases, in several cases, actually, there is a lot which mid-IR can leverage from the existing PIC ecosystem or PIC supply chain. Of course, the materials are different, and there are some unique challenges which have to be solved, but there are few which already exist in some shapes and forms. So which is a positive sign.
There's a question that comes from what you were saying there that I might hold to the end, actually, which is I feel like with this kind of area of debate, it's one of those things that feels forever slightly ahead of where we are. E.g., when does this kind of reach a kind of tangible kind of application area, e.g., when does it start to scale? And I wonder whether if I said it's a year away, or if it's 2 years away, or it's 5 years away. I'm kind of interested in the timeframes, but I might let you just have a think about that, and we'll come to that question at the end, because I am keen to know when we have this discussion again whether whether the evidence will be there. But I wanted to just pick up on something else you talked about, Abdul, which is about the foundry ecosystem. And there was a question that's come in which I think kind of fits perfectly with that for everybody, and I might go back to Emre just quickly on this one to start it off. To ask about how mature we think the foundry ecosystem is for mid-IR PICs, and basically what's needed to make fabrication as accessible as it is for silicon photonics in the near infrared. So Emre, I'll go to you first, if I may.
Yeah, surely. So as long as the technology platform, the material platform allows you to use the same technique that you use for like datacom, telecom, silicon chips, then it won't be really big shift in your fabrication. But it is not the case in mid-AR applications. The one that I mentioned, most of the let's say mainstream foundries are using let's say standardized processes where you can have some building blocks in that platform and you actually start designing your own chip. But in mid-AR platforms, we still lack, Richard actually mentioned, like building blocks. There isn't enough, or let's say the same number as building blocks you can find like silicon nitride platform and SOI platform for C or O band wavelength range. So first of all, the devices should be improved and accessible, where you can actually enrich your applications by connecting them. The second is, again, material property can be challenging in this case, should be more mature in terms of fabrication quality, like a germanium crystal mismatch with silicon can create easily fabrication issues. So it is a matter of iteration and processing, optimizing your fabrication process first, and then go after the applications later.
Okay, thank you. Abdul, what are you seeing in terms of that foundry kind of view? I appreciate it's sort of a little bit further away from perhaps some of what you're dealing with, but what would your take be in terms of that ecosystem?
I think on foundry side, the positive thing is that there are a lot of options available. Okay, the access to these platforms exist in different forms. The most well-known and the most cheapest, or you can call it economical option, is to, of course, put your design on a multi-project wafer runs. Okay, there are few players who are already offering it. Cornerstone, Emre's institute is already offering it, and not only on one platform, actually on more than one platform, they are already offering it, right? So, but there are others as well who do not offer it in MPW form, but they would like to have more bilateral engagement, and so and these platforms are, I would say, quite mature, where you can really do your first prototyping and work in tandem with these foundries, to escalate the maturity level as you do these exercises together with them. So the Emre also mentioned about standardized process flows, which are of course necessary if you want to confine your development in a certain parameter. Otherwise, it becomes too big of a playing field to address. So you have to standardize in some shape or form. And then when you standardize it also, to reach the maturity, you need to have a certain amount of churn, like number of wafers which you churn out, because the foundry maturity is linked to the wafers the foundry produces. So this is again in an indirect manner linked to the demand side. So to summarize that there are options on the foundry side which are available. Their maturity is, I think, decent. People can access it either in MPW or in a more bilateral dedicated engineering run mode. Mostly on R&D side. I don't know of any commercial foundry, like a large volume commercial foundry offering it. It is still not there. And the reason for that is, of course, it is demand driven for those foundries. But definitely on R&D side, I mean, Ruud's organization, IMEC, has a platform in France. Leti has a platform for it. So there exist options. Maybe Vigo also has some options related to that. So and maturity is with the churn, as I told you.
Yep. Richard, do you want to just jump in there about that Vigo point and just generally sort of, what your perspective is on that question?
If I may add a few words to what Abdul and other speakers just said. Well, it is obvious that the ecosystem of mid-IR photonic integrated circuits is not mature at all at that very moment. However, it is progressing rapidly. That's my observation from the last few years, and there are there's a continuously increasing number of platforms available to researchers or perhaps also for some first trials to more oriented toward the market applications. So there are, as Abdul mentioned, platforms in scalability. There's a cornerstone offering MPW in that spectral range, if I remember correctly. Vigo Photonics will offer this within the perspective of the next 2 years, I would guess, and so on and so forth. So the ecosystem is prepared for this market pool, or we are doing a lot to prepare that ecosystem to fill the requirements of the market and demands of the market.
Okay, thank you. And Ruud, IMEC, as Abdul was saying, is already kind of in this space a little bit. I mean, what how critical is it in terms of kind of the company strategy, and what do you see kind of emerging over time?
Well, critical in the sense of strategy, I would say it's more integrated photonics as a whole is critical as part of IMEC strategy, and as part of the integrated photonic roadmap. Of course, we're also looking at a broader range of wavelengths and applications. And yeah, the mid IR is quite broad, right? So you have the close to near IR, let me call it. So just above 2 micron. Then you have the standard sort of CMOS or CMOS compatible processing, which is still acceptable. Then you can go into germanium, which is beyond that range. And yes, we're looking into it, but also from our side, it's really customer driven. So if there's no customers that are interested in it, then also IMEC will not do too much work in it.
Yeah.
Yes, we're working on it, but as long as there's no customers driving it, there is
a limited
lower production on the site.
Yeah, well, again, another English phrase that probably won't translate very well is the chicken and the egg, right? You need the customers to try and build the business case, etc., etc. Okay, just jumping around then a little bit around this topic, because some of the questions that have come in have helped us kind of get further into this than we'd planned, which is good. I wanted to talk about supply chain, which of course was, a big issue, particularly a couple of years ago as we were coming out of the pandemic. The development and deployment of mid-IR PIC technologies will obviously influence the resilience of the semiconductor supply chain. What do you think is the impact most likely to be, and where will the friction occur? Is it going to be technical? Is it going to be technological? Is it financial, geopolitical, or is it all of the above? So how does this kind of evolving kind of market opportunity, albeit an opportunity that we can't entirely fix on at the moment, likely to kind of create issues around wider supply chains? Abdul, I'll go to you first, if I may.
Yeah, so maybe before answering this question, a little bit adding on to to the previous question, is that of course in Europe, the PICs Europe, their mid IR is a dedicated theme. right? So it little bit hints on the priorities of this very big European initiative of pilot line PICs Europe. So, and then the supply chain for mid IR, I think it is not specific to mid IR. I will address it more broadly for the bigger bucket of integrated photonics. And actually, there are two possibilities. I'm sharing how I look at it. Maybe the others look at it differently. So, as I said earlier, that the photonic chips are one very key element of the total solution. It is not the solution, but it is one very important part of the solution. And then you have everything around it. So it is very important for the integrated photonics ecosystem or the integrated photonics supply chain to be very well correlated with the other associated supply chains. For example, if it requires semicon supply chains, then we have to work in good sync with them. So we cannot live in a bubble of our own as integrated photonics supply chain. In any case, the critical mass which our supply chain in total has is relatively small as compared to the bigger semicon supply chain. So one thing is that we have to align it with the semicon supply chain, and maybe we can leverage a lot. In some cases, we say that integrated photonics leverages the existing CMOS infrastructure. This is one example, where this synchronization is very important. Of course, then there are some specificities related to photonics packaging. The good thing is that now even larger electronics packaging houses are looking into photonic packaging, and there are also packaging houses doing photonic only packaging. For example, in our Photon Delta ecosystem, we have companies specializing in photonics packaging only, and this is agnostic to any kind of photonic chip, say silicon nitride or germanium based mid IR platforms or silicon based platforms. I think on the design side, I'm going through layer by layer of the supply chain. Then you have the design vendors. I think any design software which can design a chip for transceivers can equally well design chips for mid IR, apart from some very specific things, maybe related to lasers, maybe. So the maturity of the supply chain is of course still not there, but if we hook it up to a more mature partner, say it the transceiver supply chain of PICs or the broader semicon supply chain, I think this will get augmented for sure. At least this is how I look at it. And yeah, one thing you mentioned, the geopolitics, and I think one application which we did not touch is the defense application, right, which is also very interesting for mid-IR applications. And now with the geopolitical situation, maybe some defense companies will like to seek some applications through mid-IR technologies, and then maybe the technology will become even more critical to be onshored and to operate in a more sovereign manner.
Okay, thank you. Yes.
Mhm.
So Abdul gave you a kind of an open kind of goal there if you want to kind of contradict him or agree with him. So a quick fire round because time is marching on a bit. Richard, anything to add to that or disagree with?
In general, I agree with nearly everything what Abdul said, and apart from that, I do believe that there is a significant positive influence of broadening the spectral range of photonic integrated circuits and developing the new technologies, because it moves. In general, the technology we have in hand beyond the limits of currently available technologies, which is always good. So we are gathering new knowledge, we are broadening the ecosystem, we are broadening the scope of expertise in the field, and we are also broadening the potential application fields. That's obvious, specifically with respect to what Abdul mentions about defense-oriented applications. Extremely important in those days, unfortunately.
Yes.
But it is also a negative influence to the ecosystem, because moving toward new technological platforms, toward new materials, we are more and more dependent on the raw materials, and the raw materials are well in different places, but not necessarily in Europe. only. So this defines or potentially might define a new dependencies on foreign countries and foreign economies, and everybody knows that semiconductors are now weaponized to some extent. So it's a new weapon with respect to economy and availability of resources. So this creates some sort of danger. So that's my thoughts on that.
Okay, thank you. Ruud, I'll come to you on this as well, if I may. Any kind of sort of issues around this you'd like to kind of agree with or disagree with?
No disagreement. So I see the same topics as has been raised. So it's mostly the 3-5 materials. They are scarce and not necessarily always available. At the moment, they still are, but who knows what will happen tomorrow. So that's the potential bottleneck. On top of most wafer suppliers are also not in Europe. So it's not even the material itself, but also the next step in the material. So it's the wafers and other materials that are not necessarily fabricated in Europe. So then, yes, those are the bottlenecks, I would say.
Okay. And Emre, just finally over to you quickly.
Yeah, surely. I also agree. Just small comments. Of course, mid-AR applications with maybe new materials, different materials will kind of diversify the semiconductor supply chain, and I see also there's lots of opportunities for them because sensing applications are opening new areas of applications, so they can enrich their portfolio, the range of the applications. So rather than they will stress the whole supply chain, I see the kind of complementary, adding a new material system and new applications, then they can actually work on different applications rather than mainstream ones.
Okay, thank you. I'm going to quickly go to a question that's just come in. It's a kind of slightly more technical question, so maybe I'll just go to Richard perhaps on the first instance. So somebody has asked with like near infrared high-speed requirements for telecom, etc., do we have similar requirements in terms for speed for mid-infrared, especially in the detector part, or even millisecond speeds are enough? So how different is it, I suppose, is the core of the question.
Depends on the application, to be honest, because if you are considering sensing, everything might be realized in a really slow manner. That's my understanding, and that's my opinion. That, however, there is a field also attractive for mid-IR photonic integrated circuits, which is free space optical communication, for which mid-IR might be extremely attractive as a wavelength, to some extent immune to fog or rain or stuff like that in the atmosphere. And considering that very applications, there are definitely limits set by the technology. However, what we have discovered and what we have tested so far, it's answers to that question in that sense that we are able to provide a relatively efficient free space optical communication links up to 10 G per second even. So it's quite satisfactory for the free space optical communication, I would guess. So 2 gigahertz on the side of the detector or quantum cascade lasers is not an issue at all at that very moment. So we can move beyond quite easily. However, definitely the limits are set much lower than in classical 1.55 transmitters.
Okay. Right, thank you. That's great. Right, I'm going to ask just the panel another question then about the kind of quite a sort of an on-the-ground question, really. What are the keys to optimal implementation of mid-IR PIC sensors for application developers and engineers? So, how, when they're actually working on this, what do they need to be doing? Maybe give me one example of something they need to really think about. Ruud, I'll come to you if I may first. Oh, you're still muted.
There we go. Yes. the shortcut didn't work. Yeah, so that's always the good question, right? I think yeah, it really depends on the application that we're looking at. So you have to have the right wavelength for your particular application, and then the equipment around it. Do you have the right detector, the right light source, the right modulator if you need it, the right PIC integration platform? So those are the standards, which is not only for mid-IR, but pretty much for everything, with the exception that in mid-IR, it's more difficult to find the right equipment.
Okay. So there's a bit of a preparation advice there coming through from Ruud on that one. Abdul, over to you, please.
So I would say this is a very general, for any application builder trying to do mid-IR, I think colleagues mentioned earlier the value proposition of mid-IR, stronger absorption line in longer wavelengths, which makes it as an interesting platform. I would say that it is always interesting to have a more top-down approach, not a bottom-up approach where you start with the technology and then you try to match it with some application. This is always, I find it a more challenging route. I think going top-down, first finding the relevant problem for which mid-IR is absolutely the key technology, and then also investigating if PICs are really the most viable vehicle to do that. There is no need to be unnecessarily married to PICs if PICs are not the right medium for you. And I think a simple litmus test for me, this is again my own personal opinion, that if I have to build an application and if I have, say, less than 5 building blocks which I want to have on chip, then I will not try to integrate it on chip. This is the power of integration, is when you integrate certain number of diverse building blocks on a chip in a compact manner. Otherwise, there is no shame in just making a meander of fiber and using it as a sensor. So this is, my very, very strong opinion about it. Use integration where it is necessary. Don't use it where it does not make any sense. And go top down, not bottom up.
Great, fabulous takeaways. I love it when people give us nice, pithy, simple sort of quotes that we can use like that. Emre, see if you can be that for us, please.
Yeah, surely. Well, it starts all about the material choice at the beginning, because it will define the footprint of your devices on the chip. So how densely you can have photonic devices will depend on the material choice. Then when we talk about like commercial sensors, then of course co-design is key, because as I mentioned, these sensors will be deployed in some locations with probably severe conditions, like in the ocean, and your circuit as whole will be stabilized in order to perform correctly. And it is not trivial in photonic integrated circuits in general, because the light and the circuits are very sensitive to the environmental turbulences surrounding of the chip. So one thing is how to stabilize your chip in real conditions. And of course, the material choice comes after, when you design your own chip. All the sizes and the fabrication processes will depend on the first choice that you make.
Okay, thank you. That was great. Richard, over to you then to wrap up this question.
To comment this in a little bit different way, because I do believe that application designers are really smart guys and very creative. So I do believe that they can design nearly everything, and everything we should provide them with is the well-established technological platform, common platforms, perhaps advanced design tool chains, an open access manufacturing possibility. So that's the issue. If they will be provided with the building blocks, if they will be provided with the appropriate technology, they will do marvelous things.
Thank you. That was great. Right, we're on the hour, so I'm going to go to one more question, if I may, and this is, I guess, what one would call the wrap-up question. Obviously, we've talked a lot about the development of the technology and where it's going. So I wondered if each of the panel could highlight a prediction for where this market goes. Where do we see mid-IR PIC sensing evolving? And when we think we get to that killer application, which is scalable. So kind of when does this stop being an abstract discussion about what is possible into something that we are seeing at kind of mass production levels? So I'll go to Abdul. I'll start with you, if I may.
Yeah, so Mark, this is a crystal ball exercise. So
Absolutely.
difficult, and you are recording it also. So
I won't hold it against it. Nobody will be replaying this in a year's time, I promise.
So I think given that mid-IR really brings some unique values, especially on the sensing side, say it healthcare or in general for environmental sensing. I would say that, and I agree with Richard that the ecosystem is shaping up, the supply chain is shaping up. So it's about maturing one killer app. So in my view, I think in next 3 to 5 years, we will definitely see few promising use cases where mid-IR really makes sense. And also there have been some failed attempts, which Rod has mentioned in the past, and I think there is nothing better than failure, because the type of learning it provides is incredible. So seeing these factors, I would say in a matter of 3 to 5 years, we should definitely see something interesting happening.
Okay, thank you. I promise we won't hold you to that. Rude, do you want to come up with a different answer or agree entirely? Up to you.
The 3 to 5 years sounds reasonable, yes. And I think the two killer apps that I foresee right now are indeed, on the one hand, the failed attempt of our US friends. Because there's still a lot of interest also from very, very big players, right? So that's the number one word that I see going places. The other one is really in people's homes. All over the world, not only in Europe, but all over the world, there's still a lot of gas lines going into people's homes. And you need to be safe. So yeah, especially where it comes into your house, you want to have a detection. And in Netherlands, it's not needed to have a gas detection. It's of course safe, but it's not needed. I know from certain countries like Japan, every household needs to have a single detector for gas in their homes, running all the time. And there's many houses in Japan, and especially when you count the entire world, there's many households that have a gas line coming into their home. So that will be probably one of the biggest markets to address on the short run. And short run would be 3 to 5 years. So allowing for a bit of R&D, then going into production.
Okay, well, I will. I was saying I'm not going to hold anybody to this. Hopefully, we will be back in 3 to 5 years to see if we're right. Emre, over to you, please.
Yeah, actually, some ideas. Probably it's maybe personal wish to see more PICs in environmental monitoring applications. You know, this nowadays the policies on zero net carbon emission, so they are become more restrictive. So you really need to monitor, for instance, CO2 levels very regularly, not in the air atmosphere, but also in the ocean. So from now on, within 5 years, it will be great to see more PICs deployed in the real applications, especially for gas detection. But as I mentioned also right at the beginning, healthcare applications are also emerging because, you know, if you treat a patient with a new drug, then you don't know actually how much you need to give it. Then you need to first measure the blood very regularly and in a short time. So PICs can actually facilitate and address these problems within, let's say, 5 years, if we all optimistic.
Okay, brilliant. Thank you very much. And then Richard, over to you.
Well, considering the rapid evolution of the Internet of Things or Internet of Everything, perhaps should I say, and then all those promises defined by mid-IR photonic integrated circuits, I would guess that not later than 5 years from today.
Okay, that's terrific. Right. Well, thank you. We are unfortunately out of time. So that will bring us to the end of today's session. The online panel discussion, the one you've just been watching, will remain accessible on the Electro-Optics website. That's electrooptics.com. And then it will eventually turn up on our YouTube channel, and we'll be creating an online article. So please spread the word if you've enjoyed this and found it useful, and tell your colleagues, because it's always good to share some great content like this. A huge thank you to our 4 great presenters today. Really interesting discussion. PICs is one of those topics everybody seems absolutely fascinated by, and I love the fact that we kind of don't know all the answers yet. So thank you so much for kind of bringing a complex but slightly kind of ahead of ourselves kind of environment to life so brilliantly. And thank you also to the Electro-Optics team, the production team working away in the background. Keep an eye out for future sessions. We've got one next week, which is actually on the 22nd. We're going to be talking about the future of semiconductors in a global market. So thank you everyone for taking part. Thank you for everybody watching and for the questions. It's been brilliant to have so many come through, and you know where to find us, so we hope to see you again sometime soon. Thank you, and enjoy the rest of the day. Thank you. Bye-bye. Thanks all.
Bye.
Thank you.
Thank you.